Stress strain diagrams brought to you by Oregon Tech. A stress strain diagram is the graphical comparison of stress that is in the y-axis and strain that is in the x-axis. Stress, which is usually expressed as Greek letter sigma, is measured as force over cross-sectional area. For example, in this rod P is the tensile force acting on it, and R is the radius of the cross-sectional area. To calculate stress, you divide the P, which is the force, by the cross-sectional area. Strain, which is most commonly expressed as Greek letter epsilon, is calculated as the ratio between change in length divided by its initial length. For example, a metal bar is initially 1 meter long. It is put under tension and stretched out to 1.1 meters long. The strain of that would be 0.1, and the strain is proportional, so it is unitless. The yield point is where permanent deformation starts to occur. It is where the elastic region ends and the plastic region begins. The factor of safety is the ratio of the yield point stress divided by the desired design capacity. For example, if you have a load of 500 psi applied to a rod, and you wanted a factor of safety of 2, you'd want a rod with a material that's got a yield point that is at least 1000 psi. The elastic region of the stress strain diagram is where the graph is linear all the way to the yield point. In the elastic region, the material is under forces, but the deformations are not permanent. A rubber band has a very large elastic region, while an aluminum wire has a very short one. The proportional limit is where the line stops being linear and begins to curve. The yield point and elastic limit follows shortly after. The plastic region of the diagram is where permanent deformation occurs. For example, if you were to take a spoon and bend it, if you bend it a small amount, it'll bounce back to its original shape, while if you put a lot of force on it, even when the force is removed, it will still retain some of its deformation. Ultimate strength, also known as tensile strength, is the maximum stress a material can withstand without failure. It is the highest point on the diagram. The reason the graph proceeds to drop after the ultimate strength is because the cross-sectional area starts to decrease as the material starts to experience plastic deformation and sometimes necking before its final fracture.